So I'm spending a lot of effort trying to understand bilinear mapping and what actually does it give us. And so I've gone through the group signatures white paper, and if you're familiar with that, it's basically a way of taking multiple uh, data messages, multiple messages, and actually have them signed and being rolled up into part of a group. But before you get into that, you actually have to understand the notion of bilinear mapping. Um, there's a lot of preliminary stuff that I've been working on, but I just want to give you a sense of how the proofs work with bilinear mapping. So in the case of the paper, they've actually simplified it to use one curve, G1. And what I am trying to depict here is that even though it's one curve, it's used in two instances. So I'm calling it to G1 and G1. You see it there. And then you see on the far right, G1 times G1, or GT, which is the extended field. And to help with the understanding, I decided to show the two curves on the left mapped over real. That's basically the elliptic curves that you're probably quite familiar with. And then the final depiction is actually with the discrete map, which is XY, which actually looks like a bunch of random points. So the idea here is that bilinear pairing, you're actually taking points on two curves and doing an operation, and it maps to a distinguished point, as you can see on the right-hand side. So you have these 2 points that are seemingly unrelated. If you can see A and S, and you do an operation, it maps to that distinguished point. Then you have those other 2 points down below, P and M, and to the exponent of A, it will map to the same point as well. And that's basically the basis of the bilinear proof. So mathematically speaking, the one that's used in the group signatures is basically the pairing of P and S and A and M. And if they actually come out to be the same or verified, then you know you've got a proper proof. Why? Well, let's just do some quick math based on like the theorems of bilinear pairing, bilinear pairing. So you have the public key, and instead of the signature, I put an AM, which is actually how you calculate the signature. And then on the other side, A, which is AP, and M. And when you transform that, you get APM, which is the same as APM, or e to the PM to PM to the A is the same as PM to the A. So basically what that boils down to is that you have a proof, what's called a Diffie-Hellman tuple, of 4 public values. P, which is the generator key, the generator value. You have the signature, you have the public key, which is A in the case that I have here, and then M, which is actually a hash of what's to be signed and mapped to a point. So the key thing here is that these 4 points, or this quadruple, can only be generated if the secret of A is known. And the convention that I've adopted here is that anything that's in capitals is public for everyone to see. Anything that's in lowercase, in this case it's just the letter A, is the secret. So here's the nub of the whole proof, is that those 4 numbers, P, S, A, M, they look like they're totally random, but they're actually related because they actually all map to, if you do the special operations, they map to that distinguished point. You can only generate that those 4 values if you have the secret A. And so again, you use the verification to say, well, the pairing of P and S, you do the calculation, and the pairing of AM, it should map to that same distinguished point, and that verifies to true. And as I said, it only holds true if these numbers are generated by a secret A. And then, of course, there's the question of how do you know if it's the right person that's generating that signature? Well, that's pretty simple. That A is actually the public key of A times P, and that's classic public-private key, and the secret is A, which is the private key. So once you've actually verified the signature, or do the verification with this proof, you can simply challenge whoever's providing that with you with a typical challenge and response. And that's it for bilinear pairing. I know there's a lot of basic stuff that needs to be covered, but I just wanted to give you an overview of bilinear mapping.